This is part 4 of the Chapter 2 lecture notes. And just reminding you what we saw on at the end of the last lecture. The water molecule is formed by sharing a pair of electrons between the oxygen atom and 2 hydrogen atoms. So by sharing those electrons, the hydrogen atom here, it has a complete valence shell because it only needs 2 to fill its first energy level. The second hydrogen atom also has 2 now that it's sharing with oxygen. And then oxygen has 8 because it's got 2, 4, and then 6, 8. Now that it's sharing 1 with each of the hydrogen atoms. So all atoms in this water molecule are satisfying the octet rule by sharing electrons and forming covalent bonds. Now, what you saw here was single covalent bonds. If you look here, this single line represents one pair of electrons. One electron from hydrogen, one electron from oxygen. And here, what you're seeing is 2 oxygen atoms combining to form oxygen gas, which is oxygen gas is a molecule called O2. And that forms by sharing 2 pairs of electrons between the 2 oxygen atoms. And by doing that, each oxygen atom has 8 total electrons in its valence shell. So this is called a double bond. The bond that we saw with the water molecule, those bonds were single bonds. So we've seen double and single covalent bonds. You can actually have triple covalent bonds. Covalent bonds are the strongest chemical bonds, but now we're looking at ionic bonds, which are a little bit weaker, but they form in a different way. Ionic bonds form when atoms give up or gain electrons, and then they form charged atoms, which are called ions. And the ions with opposite charges are attracted to each other. So sodium, if you'll recall, has 2 electrons in its first energy level, and then 6 electrons in its second energy level, and 1 electron in its third, I'm sorry, 8 electrons in its second energy level, and 1 electron in its third energy level. So if it were just to get rid of that 1 electron from its third energy level, its second energy level is already filled with 8 electrons. So that's what happens. Sodium is in group 1 of the periodic table, and elements in group 1 have 1 valence electron, so they just tend to lose that one. And by losing that valence electron, they now have 1 less negative charge. So before losing that electron, sodium had 11 positive charges from the protons and 11 negative charges from the 11 electrons. When it loses an electron, now it's going to have 10 negative charges. So it will have an extra positive charge. And that's where sodium gets its positive charge from. So now that sodium has an extra positive charge because it lost an electron, that electron that is lost can be gained by something like a chloride ion if the chlorine atom is nearby, because chlorine has 7 valence electrons, and by gaining 1, chlorine will now be the chloride ion, and it will be stable. It will gain that 1 electron that was lost from sodium. By gaining an electron, it gains a negative charge, and we know that opposites attract. So ionic compounds form when positive ions and negative ions are attracted to each other. The positive ion loses an electron and the negative ion gains an electron. And why do they do this? They do this to achieve a stable octet formation. A review of covalent bonds. We also need to talk about how the electrons are shared. If electrons are shared equally, we call them nonpolar. When electrons are shared equally, they are nonpolar covalent bonds. But when they are shared unequally, in other words, one of the atoms has a stronger pull on the electrons than the other, then we call them polar bonds. So polar covalent bonds, like in a water molecule, are covalent bonds in which there is unequal sharing of the electrons. Unequal sharing. So for example, the water molecule, the oxygen has a stronger hold or a stronger attraction for the electrons that are being shared than the hydrogen. So the oxygen actually carries a slightly negative charge. I don't know if you can see it in the picture, so I'll draw it. That lowercase delta with a minus means slightly negative, and the oxygen end of the molecule holds a slightly positive charge because it has less of an attraction for those shared electrons. So polar covalent bonds form when electrons are unequally shared and one of the atoms has a stronger attraction for the shared electrons than the other. Now, water is a great example. And when we say that oxygen has a stronger attraction, we say that another way of saying that is oxygen has a higher electronegativity than hydrogen. That means that it has a stronger attraction or a stronger pull on the shared electrons than the hydrogen does. Now, methane and carbon dioxide are nonpolar covalent molecules. And that is where the atoms share the electrons. The electrons that are being shared are shared equally. So nonpolar bonds have an equal sharing of electrons. And the reason this is important is that polar compounds or polar molecules like water don't mix with nonpolar molecules like oil. And this is an image of oil and water. Oil would be the nonpolar molecule and water would be the polar. So what happens is substances that are also polar, like water, will dissolve in water. And substances that are ionic, like table salt, sodium chloride, will also dissolve in water. But nonpolar molecules will not dissolve in water. Now we're going to talk about weaker chemical bonds, hydrogen bonds, and van der Waals interactions. So ionic and covalent bonds are the strongest chemical bonds, and they require energy to break those bonds. Weaker bonds don't require energy to break the bonds. In hydrogen bonding, we typically discuss hydrogen bonding in relation to water molecules because it's the interaction between the positive hydrogen end of the water molecule and the negative oxygen end of the water molecule. And that oxygen end, it doesn't have to be oxygen. It can be the negative end of any molecule, that has hydrogen in it. So often hydrogen bonding occurs between water molecules, and we will look at a slide and look at an illustration of that in a minute. Van der Waals interactions are weak attractions or interactions between two or more molecules due to changes in electron density. And we may or may not come back and talk about van der Waals interactions, but we definitely need to discuss hydrogen bonding because water is essential to living things. Water makes up 60 to 70% of the human body, just depending on how hydrated you are. It is the most critical molecule for life on Earth. The presence of water is what enables life to exist. The reason it is the most critical molecule is that it is polar and that it can form hydrogen bonds. And we will talk about why. Now, this page shows you an illustration of hydrogen bonding between water molecules. So this is one water molecule here, and the bond between the hydrogen end, which is slightly positive, of the molecule that I circled, and the oxygen end of the bottom water molecule, which is slightly negative. That bond is shown by a kind of a dashed line or a dotted line because it is a weak bond, but it's what holds water molecules together. And what will happen is in any area where there's water, whether it's a droplet of water or whether it is water that forms a pond or a lake or even the ocean, the water molecules that are together are attracted to each other in such a way that the hydrogen ends face the oxygen ends. The hydrogen ends of one face the oxygen ends of another. And you can see that. Here's 1, 2, 3 water molecules, and they are oriented so that the hydrogen ends of the top two face the oxygen end of the bottom molecule. And that is because hydrogen is slightly positive and oxygen is slightly negative. So hydrogen bonding is the key to the 3 states of water: liquid, gas, and solid water, of course, which is ice. Gas is water vapor. So it is the hydrogen bonding that forms the crystalline structure of solid water or ice. And the way that the water molecules arrange themselves when they form ice makes ice less dense than liquid water. Most of the time when you melt a solid, the melted form, which is the liquid form, is lighter, it is less dense, and the solid form will sink in the liquid form. Any metal that you think about, if you melt a metal and then you drop the solid metal into the liquid metal, the solid is going to fall to the bottom. But water is different. The solid form of water floats on the liquid form. And this is due to hydrogen bonding. Another thing is that water has a high heat capacity. That means that there's a definition for heat capacity. It's specific heat is the amount of heat 1 gram of a substance must absorb in order to raise its temperature 1 degree Celsius. But sometimes that can be hard to understand. So what does it mean? It means it takes a long time for water to heat up, and it takes a long time for water to cool down. Now, if you don't believe this, one thing that you can do is, it's summertime, so go to the beach in the heat of the day at 12 noon and walk on the sand barefoot, and you will know how hot the sand is. But the water, which is facing the same, which is absorbing the same heat from the sun, is going to be cool to your feet. So as soon as you get across the sand and get into the water, it cools your feet off. That is because the sun can heat up the sand a lot faster than it can heat up the ocean water. It takes a longer time to heat up that water. And you can do the same thing at night. You can walk on the sand and the sand will feel cool to your feet, but the water will actually feel warmer than the sand. And the reason is not that the water warmed up, it's that the sand has cooled faster than the water has. So the water has really pretty much maintained more of a stable temperature throughout the day, and the sand has heated up and cooled down a whole lot more drastically. Another thing that's very similar is that water has a high heat of vaporization. So again, it takes a longer time to evaporate water than it does other substances. It takes a lot more energy to evaporate water than other liquids.